I'd like to start my presentation. The title is Embrittlement by Tramp Element and Determination of its Allowable Content for Electric Furnace Steels. This is today's content. First, I talk about introduction. There are two ways to make steel materials, the blast furnace method and the electric furnace method. Compared to the blast furnace steels, the electric furnace steels can contain impurities like tin or copper, but emit less carbon dioxide, as the graph below shows. And this pie chart shows the steel industry emits more carbon dioxide than any other industry. Therefore, it is important to reduce emissions from the steel industry in order to promote a low-carbon society, and the electric furnace method is attracting attention as one of the ways to achieve this. However, as shown in the graph, the share of electric furnace materials in crude steel production has not increased, especially in Japan. So the large and high-grade buildings require higher toughness than small buildings. Therefore, electric furnace steels containing Tramp elements are not often used. Next, I will explain why electric furnace steels are not used in the large building field. First, electric furnace steels contain impurity elements that are not contained in blast furnace steels. In particular, tin and copper called Tramp elements are difficult to remove by refining. And it is said that steels which contain tin can become embrittled when tempered in a certain temperature range. And in the field of large structures, large heat input is used for welding joints. In the welding, temper embrittlement can occur in the field affected zone. Therefore, electric furnace steels containing tin have rarely been applied to the field of large structures. It is said that steels with temper embrittlement fracture at grain boundaries. Brittle fracture can be roughly divided into two types, intergranular fracture and transgranular fracture. The form of fracture depends on which is more likely to occur. First, now I will explain the mechanism of grain boundary fracture caused by tempering of steel containing tin. First, tin segregates to the grain boundary in a specific temperature range. This is the embrittlement temperature range. Next, microcrack occurs, which is starting point of fracture. Microvoids are formed around the inclusions and atoms on the surface of the voids migrate to the lower energy interface, causing the voids to expand and microcracks to form. The crack propagates through the grain boundary because the binding force of iron is weakened and the grain boundary becomes easier to fracture. This is how intergranular fracture occurs. Next, I will explain why temper embrittlement occurs during welding. To begin with, tempering is a process of reheating to a lower temperature than quenching to improve toughness. However, when tempering is done in a certain temperature range, the toughness can be adversely affected. This is called temper embrittlement. In the case of welding, temper embrittlement occurs in the heat-affected zone of the welding. Let's look at an example. Consider the temperature change in the blue area, which is part of the weld heat-affected zone. If it is close to the bed, the temperature in that area will rise to a relatively high temperature. The second time the temperature rises to a lower temperature than the first time. At this point, tempering to the embrittlement temperature has occurred. Then I'd like to talk about experiment. First of all, let me talk about the purpose of our experiment. The main goal of our research is to increase the share of electric furnace steel in crude steel production. To achieve this goal, we decided to investigate the permissible additions of tin that cause toughness loss during welding. Therefore, we conducted fracture tests on specimens with different amounts of tin and different heat treatment conditions. First, the chemical composition was prepared with three different amounts of tin, 0.01 and 0.1 and 0.2% with and without boron per each. Boron is more prone to segregation than tin, so boron may prevent determination of toughness due to tin segregation. So the boron was prepared. Next, the heat treatment was applied as shown in the figure. Welding should be done, but for simplicity, we used a two-step high heat cycle. The first cycle was heated to 1400 degrees C for 1 second, and the second cycle was held at 400 degrees C, which is the typical temperature of temper embrittlement for various lengths of time. The toughness was evaluated by performing a three-point bending test and calculating the CTOD. CTOD is one of the fracture toughness parameters such as stress intensity factor. Then for each steel grade, the ductile to brittle transition temperature was calculated from CTOD and its heat rate condition, and the difference from the single cycle transition temperature, delta T, was calculated. The lower the transition temperature, the better the toughness. So the smaller the delta T, the better the toughness. This graph shows the change in transition temperature for each tempering retention time. First of all, when the tin content is more than 0.1%, temper embrittlement clearly occurs when the holding time is short, whereas the change of 0.01% of tin still is flat. It can also be seen that the toughness of the steel where temper embrittlement occurs improves as the holding time increases. This is probably due to the fact that the effect of tempering on toughness is greater than the effect of temper embrittlement. Then I talk about discussion. Previous studies show that tin segregates at grain boundaries and causes intergranular fracture. However, only cleavage fractures were observed. Therefore, we considered about why did transgranular fracture occur and why was the origin of fracture in the grain instead of the grain boundary. As mentioned before, the form of fracture is determined by which is more likely to occur. First, let us consider the susceptibility to fracture before tempering, tin segregation. Basically, in base plate, these locations are piled up at the grain boundaries, and this can be the starting point for fracture. In addition, transgranular fracture is more likely to occur. On the other hand, in the heat-affected zone, these locations are piled up not only at grain boundaries, but also around precipitate. Therefore, the probability of the origin of fracture within the grain boundary increases, and the probability of transgranular can also increase because the fracture starts within the grain. Next, let's look at what happens after the steel has been heated to the embrittlement zone and tin has segregated. In the base plate, tin is segregated at grain boundaries, and since tin weakens the bond strength of iron, so cracks are more likely to propagate along grain boundaries. Therefore, the probability of intergranular fracture is much higher than before segregation. As a result, intergranular fracture is considered to occur. On the other hand, in the heat-affected zone, stain segregates not only at the grain boundary but also at the precipitate interface. Therefore, not only grain boundaries but also grain boundaries are weakened, and cracks are more likely to occur both along grain boundaries and within grains. So both fracture likelihoods increase. Since transgranular fracture was more likely to occur before thin segregation, so transgranular will occur in total. Finally, I talk about the conclusion. As a result, it is found that a small amount of tin does not cause temper embrittlement, but a tin content of 0.1 or more will cause temper embrittlement. In the case of large heat input, temper embrittlement may cause transgranular fracture instead of intergranular fracture, and the mechanism is discussed. Our future plans are to verify the tentative results and to model the phenomenon. Thank you for listening.